Okay, let's look at the last two on web work. Okay, so this one, all they want is the radius of convergence. We'll go ahead and find the whole interval just for a good practice problem. All right, so what are we going to do here? So this is pretty complicated sequence that we've got. So we're going to use the ratio test because this isn't going to nicely compare to any of our basic toolbox kind of series because it's complicated. So it looks like a job for the ratio test. So we're going to do the limit as n goes to infinity of an plus 1, so the n plus first term. All right, so negative 1 to the n, we know that's just going to be, in the absolute value, will be 1 in the end. So I'm going to just leave that off. Again, if it's not a negative 1, you're going to need it inside. That could make a difference. If it's negative 2 or negative 5, that can make a difference with what your limit turns out to be. But at negative 1, we know in the end that'll just be 1 and that won't affect anything. So we've got x plus 12 to the n plus 1 over 5 to the n plus 1, n plus 1 cubed. That's our a n plus 1. We're going to multiply by the reciprocal of this, 5 to the n cubed over x plus 12 to the n. We're going to combine or group things that are alike and analyze this. So first we got x plus 12 to the n plus 1 and x plus 12 to the n. Again, what are we thinking about? What does x plus 12 to the n plus 1 means? What you should imagine a bunch of x plus 12s multiplied together. Same with x plus 12 to the n. So then what do we compare? We compare how many x plus 12s are multiplied together in the top versus how many x plus 12s are multiplied together in the bottom. And it's pretty easy to see. So how does the number of x plus 12s compare? One more in the top, right? We have one more in the top. So then all n of these will reduce or cancel with the ones in the above, and then you'll have one left on the top. Gotta know your exponents, what they mean. Okay, same thing, 5 to the n in the top, 5 to the n plus 1 in the bottom. Means one more 5 multiplied together. This is a string of 5s multiplied together. This is also a string of 5s, but there's one more 5 here than there is here multiplied together. So we got one more on the top. And then we're going to have n cubed over n cubed. If we multiply that thing out, our leading term would be n cubed. Okay, so what happens to this as n gets large? Nothing, right? It doesn't care about n, has nothing to do with n. So as n gets big, it just plays itself, right? And then this one, that will go to 1. We'll have leading term n cubed over n cubed. So this will go to 1 as n gets large. So this limit, as n goes to infinity, is the absolute value of x plus 12 all over 5. In order for this thing to converge, what about this limit? It's to be less than 1. So now we have to solve this thing for x. That thing has to be less than 1 for that series to converge. Absolutely. And so we're going to solve this for x. This will tell you what we're trying to figure out. What values of x will make this limit less than 1? So what does this imply? This implies that negative 1 is less than x plus 12 over 5, which is less than 1. So now we're just solving for x. That's like an equation, but we got 3 sides, right? So we can multiply by 5. And then subtract 12 from all 3 sides, right? So minus 17 less than x less than minus 7. Okay, and so what would we do? So if we really wanted to get the whole radius convergence, then we take negative 17 and we plug it in for x, and we'd analyze that thing. And we take negative 7, we plug it in for x, and we analyze that thing. But this question is just asking about the radius. So whether or not you're including these endpoints or not doesn't change the radius, right? The radius is the distance from the center out to the edge, whether we're including those or not. So what is our center here? What's our center? Well, it's just like that. You could do the average of these two. So it's going to be negative 12, right? Negative 12. So whatever this is, from negative 17 to negative 7, the middle is negative 12, which makes the radius 5, positive 5, right? Distance from the center out to the end. Questions on this one? So let's see what happens. Let's just do this kind of quickly in our head here. So when we got negative 7, we got 5 to the n here, right? Negative 7 plus 12, 5 to the n over 5 to the n. So when x is negative 7, we end up with this, negative 1 to the n times 1 over n cubed. Convergent or divergent? Convergent, right? How about this? Is it absolutely convergent or conditionally convergent? Conditional on the alternating. Absolutely convergent. That's right there. That's enough, right? That's a p series of p greater than 1. Doesn't need the alternating effect. Absolutely convergent. But even if it was conditionally convergent, we would still include it in the interval. What about negative 17? Negative 17 gives us negative 5 to the n. So negative 5 to the n over 5 to the n is negative 1 to the n, times another negative 1 to the n is just all 1. So this, when you put in negative 17 for x, this thing is all just becomes 1. Because you get negative 5 to the n times negative 1 to the n, which is plus 5 to the n over 5 to the n. So now we have 1 over n cubed. Convergent or divergent? That's our convergent p-series, right? So this one too. So if we were doing the interval, it would be include the endpoints. Negative 17 less than or equal to x, less than or equal to negative 7. But that doesn't change the radius, whether we include those or not. The radius is a distance, so it doesn't matter about whether that's an open circle or a closed circle on the endpoints. So the radius is 5. Questions on this example? Okay, let's look at the last one. So this one. So here we might come along here and say, for what values of x does this converge? Well, what has to happen to a sequence? What has to happen to a sequence in order for the series to converge? Has to go to 0, right? That's like the flip side of the divergence theorem, right? If that thing doesn't go to 0, then game over, right? If that thing does anything but go to 0, so this is, wow, x would, what does that x have to be? Okay, so what if it was x was really super small, 0.000001? Yeah, but I mean, basically this together is 18x to the n. So the 18 really doesn't do anything. Because we could think about making x really, 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 really small, and we could make it small enough just to cancel out the effect of the 18. So the question is, what's going to win here? A really, really small x raised to the n power, because that's going to get small, or n factorial, which is going to get big? What's going to win? Well, we do the ratio test to find out. Because we could imagine super, super small values of x, this going to 0, this going to infinity, So that's an indeterminate form. All right, so what we get here is, and I'll just go ahead and do it that way, 18x to the n plus 1 times n plus 1 factorial over 18x to the n, n factorial. So since we don't have a actual start with a ratio here, we'll go back to the a to the n plus 1 over a to the n. And what will we get? One more 18x and n plus 1, right? So n plus 1 factorial is n plus 1 times n factorial. N factorials go away. So here we are. What is that limit? As n gets large. Yep. So pick x to be any value, and this will be infinity, except there's only one value of x that will prevent this thing from going to infinity. And that's x equals 0, right? If x equals 0, then the limit is 0, no matter how large n gets. But any other value of x, non-zero, n will get really, really big, and then that whole expression will get really, really big. So we have kind of the trivial case where if x equals 0, you get every term of the sequence to be 0, and so that's convergent to 0. So our solution interval looks like this. And so what's the radius of a single value? It has no radius, right? So the radius would have to do with having some finite width of an interval. So we don't have any width to the interval. Radius is 0. So we should say infinity except questions on this one? Okay. So we are experts at power series. So let's continue on this track here. So we saw that a power series is essentially, what is a power series essentially? Well, how can we think of it in terms of things we knew before? Oh, by the way, got my list. So what did we say? We can think of a power series in terms of things we learned before calculus. Okay, so polynomials already have changing coefficients. So how is it a little bit different than a polynomial? You know, anything that makes it different? Yeah, so it's like a polynomial with an infinite number of terms, like every single exponent of x, because our exponent of x is the n, right? So we think of we can think of a power series as a function, particularly an infinite polynomial. So this leads us to what other kinds of functions could we represent with power series? So we know we can represent polynomials with power series. What other kinds of functions could we represent with power series? So let's look back at the geometric series here. And so recall we got this is the n starting at n equals 0 version of the geometric series, n equals 0 to infinity, ar to the n. And we know that when r is within that interval, the sum of all infinitely many terms would be a over 1 minus r. Okay, we've seen that before. So consider this function, 1 over 1 minus x. 1 over 1 minus x. Could we represent that as a power series? given this definition or this the geometric series, how might we consider 1 over 1 minus x, or how might we relate that to a geometric series? Okay, so let's take it one step at a time. So how can we see this as geometric series? Do you see any relationship between this and this? Yes, sir? Yeah, so we can think of this as like, and this is where he went as well, just, do you see that that looks just like a over 1 minus r, right? Where a is what? A is 1, and? Instead of r, we have our r is x, right? So then, that leads us to what power series? Or what, yeah, so what series then could we set up? If a equals 1 and r equals x, where's Alyssa Madrid? Is Alyssa here? Yeah, so what series could I set up for a equals 1 and r equals x? Was it? X to the n, 1 times x to the n, right? A is 1, r is x, starting at n equals 0. So look, so this series is equivalent to this function, right? So n equals 0 to infinity, x to the n is equivalent to this function on one condition. What's the condition? Yeah, so this is only going to work, it's only going to work when x is between -1 and 1, right? Because if x is outside -1 or 1, this thing diverges, right? This is a divergent, just blows up. So in that interval from -1 to 1, this is going to equal this sequence. So you see this, think what, right? See this, think what? Write it out. What does that equal to? Where's Sinuo? Pan? Sinuo? Yeah. Did you get it? Tell me what this series is equivalent to. Uh-huh. And when do I stop? Never, right? Is that what you got? I think I have all this in a nice PowerPoint version. So, if x is between -1 and 1, this power series will be the same as that function. Let's take a look. Does the rationale make sense? Does the reasoning make sense? Any questions on that? So let's take a look at that. So here I've graphed 1 over 1 minus x in blue from -1 to 1. And it has an asymptote at 1, so this will shoot off to infinity as you get very, very close to 1. Okay, so now here, what do I have? I have that series, x to the n, but I'm going to show it to you as in partial sums, right? So when n equals 0, what is it going to do? It's just going to show the first term, which would be what? 1, right? Just 1. So here's just the first partial sum, which is just the number 1. When I do the next partial sum, what function will we have? So that the second partial sum will be what function? So remember what this was again? What was this again? Was 1 plus what? X plus the whole power series then goes on and on. So the second partial sum would be what? What would be the second partial sum of this series? Just 1 plus x, right? So when I set capital N equal to 2, or sorry, capital N equal to 1, I'm going to get the first two terms. When little n is 0 and little n is 1, and that's the second partial sum. And I get 1 plus x. Okay, third partial sum. 1 plus x squared. So let's take a look at that. Here's the third partial sum in red. What happens? Every time I add another term, I get a better approximation of the power series, right? With the sequence of partial sums is going to converge on the actual sum of all infinitely many terms. So every partial sum, the more terms you add, you get a better and better approximation. So you're going to see this red curve start to take the shape of the function 1 over 1 minus x. So here's the fourth partial sum, fifth partial sum, sixth partial sum. And so now we're around 0. We're doing really, really good, right? You can't see the difference. As we get off close to 1 and negative 1, kind of peels off a little bit. But again, the more terms that you add, the longer your partial sum, the better approximation it is to the whole sum, or to the whole power series. So by the time I get to, there's 7. So here's n equals 10, and just flips off a little bit there at about negative 0.8 or negative 0.9. But the rest of it, pretty close. So this is showing how that power series is converging on the actual function we started with, 1 over 1 minus x. That's pretty good. There's the fifth partial sum, so that's a pretty good view of what's going on. Does it make sense? Okay, so then we can have some variations on this form. This a over 1 minus r, we know is the sum of a geometric series. So we can have some different variations of functions in the form a over 1 minus r that we can write the power series for. Okay, and although that's a really narrow class of functions, it's like 1 over 1 minus x, but it's a place to start. Okay, it's a place to start. Okay, so let's try this. X over 2x squared plus 1, and then we want to find the interval of convergence. So we knew with the a over 1 minus r, the real simple version, we know that r had to be between negative 1 and 1. But so when it gets a little more complicated, a little different, then we may have a different interval or a different radius of convergence. So we want to find the power series and find the interval of convergence. Okay, so here we go. So can we see this as a over 1 minus r? How can I write this as a over 1 minus r? Where is Amber? Nadich. Is Amber here? Yeah. X would be a, okay, x over. Yep, just all we have to do is flip it and be. Okay, but I need to be 1 minus r, so how can I make that 1 minus r? Okay, so it'll be 1 minus. Like that? Is that equal to what we started with? So how can I make this 1 minus? 1 minus negative. And now we got it, right? So I can rewrite, so basically I'm rewriting g of x as x over 1 minus negative 2x squared. And so what's the first step then to setting that up as a power series? What would the power series be? Where's Muhammad? Al Abdullah. Muhammad. Not here. Yifu. Pei. Yifu Pei. Yeah. Can we do the first step? Is writing this thing as a power series. Okay. Yeah, sure. Not over. So what's our form going to be? What's our geometric series, right? This is going to be a geometric series. A times what will it be? Where's Kaylin? Negative 2x. That? Almost. Yeah, you see it's not just negative 2x, it's 2x squared. That's good. So now we have to really know our algebra, our rules of exponents, because we want to get this into a better form here. We don't want x and then x squared to the n, etc. So what do we got? We've got, so when you have a product like say p times q to the n, what does that equal? P to the n, q to the n, right? Because it's still p, n p's multiplied together and n q's multiplied together. When you have pq n times, you have n p's and n q's. Okay, so we'll do that first. So we can do x times negative 2 to the n and x squared to the n. Okay, what's x squared to the n? X to the 2n. And so I have x to the 2n, and then one more x, right? So I'm going to what? Multiply x together 2n number of times, and then one more, and then I'm going to multiply x one more. So it's going to be x to the, so we can leave this negative 2 to the n, and then I'm going to have x to the 2n plus 1. And now we have a power series, just like your homework, just like Monday, right? And we want to find the interval of convergence for that. We want to find all x values for which it converges. And so all x values for which it converges will be all x values for which this power series will reproduce that original function, x over 2x squared plus 1. So go. So find the interval of convergence for this one. Did you get an interval? Tell me. Let's see if we're... Nice amount, is it? Square root of 1/2? Someone else get that? Do you agree with that? Okay, people are nodding. Right, so you got it. So you should have gotten that radius, or that interval, from negative radical 1/2 to radical 1/2. And so let's graph the original function for that interval. So that's what that function, that original function looks like on that interval, the blue one. Okay, and so, and what did we come up with? We came up with we had what? -2 to the n. X to the, and that was from negative, all right, let's see if this works. Let's make that red. Okay, here we go. Let's see if it works. First partial sum. When n is 0, you get x, right? So when n is 0 is the first term, x. -2 to the 0, x to the 1. Next partial sum. I was afraid of that. For some reason, this program doesn't like this form. So let's go back to the very original form. What was it? It was x times -2x squared to the, is that right? Okay, so we're going to go back to that. So how we simplified was correct, but for some reason the software doesn't like the form that we came up with. There we go. Okay, so first partial sum is x. Next partial sum would be the first two terms added together. No, that's 3. There we go. So the red would be the graph of the first two terms added together, or the second partial sum. Here's the third partial sum. Fourth, fifth. So again, with every additional term that you add, you get a better approximation. The approximation's already very, very good. You see where it looks black? It's just out at the endpoints of the interval is where more and more terms will help, right? But already in the center of the interval, very good approximation. So the 11th partial sum is good for about 90% of the interval. It's like so close we can't tell the difference. It's just right at the ends is where it diverts, right? The approximation diverts. And again, more terms added, the more terms that you add, the better and better it's going to converge on or approximate the original function, which we have in blue. Okay. I saw you guys talking. Was everything good? Okay. So original function, and then this is the 11th partial sum, is approximating that function very, very well for the 90% in the middle. Okay, another example. Any questions on that example? So let's do something a little different here. Let's look at this. 3 over 1 minus x squared. Okay, and we need to get that thing to be like what? A over 1 minus r. So this is different, right? So we can multiply out the bottom. I could do 3 over what? 1. It's going to be minus 2x plus x squared. And so what would a be? 3. And what would r be? So we could do a equals 3. And then we could do like r equals what? 2x minus x squared. Yeah, but that's not convenient. It's not convenient because then we'd have 3 times 2x minus x squared to the n. So imagine when n gets large, right? When n gets large, even if n is 100, and 100 isn't that big for n, right? So if n is 100, then what happens? The 100th term, it itself consists of 100 terms because that thing is to the 100th. So you may be able to do that, but this is not convenient. All right, so we want a different approach to this. Okay, don't want to do this. It's valid, but it's ugly. Okay, it's valid, but it's ugly. We want just one term for every n, right? We don't want this the term itself blowing up as n gets large, right? So if n is 1,000,000, then the millionth term consists of 1,000,000 terms. You see that? Because it would be this binomial to the million. So I want something else. So what we can do is we can say, what power series, or a over 1 minus r, is an easy one that's kind of like this that we can handle. So I'm going to call that a different function. I'll call that, say, f of x. So what really easy one does this kind of remind you of? 3 over 1 minus x. But that's not h. That's different. So I'm going to call it f. I'm going to call it something different, f. So here's the deal. How can I get f to be like h, to be like 1 minus x squared in the denominator? What could I do? What could I do to f so that the result would be 1 minus x squared in the denominator? Yeah, but then I have to do that in the top too, and I lose my nice a term of 3 there. So a hint is, think calculus. Calculus. What could I do in calculus to get f to look more like h? Notice I have 1 minus x. What's the power on that? It's like the -1 power, right? And what's the power in h? 1 minus x to the -2. Right? So this is kind of like 3 times 1 minus x to the -1, and this is 3 1 minus x to the -2. What would I do to f to make it be like h? Not multiplied. Calculus, calculus. Derivative, right? Derivative. This is 1, this power is 1 less than this, right? This is x, 1 minus x to the -1. This is 1 minus x to the -2. So I take the derivative, what do I get? I'm going to get, we've got to watch our signs here. So I'm going to do this. So 3 times 1 minus x to the -1. So derivative is going to be -3 over 1 minus x to the -2. Is that it? Oh, yeah, sorry. Yeah, it's to the -2, which is 2 in the denominator. Here, let's do it that way. All right, so it's going to be -3, 1 minus x to the -2. And we're done, right? Someone said no. What's that? Need to get rid of it? Am I done with the derivative? Why not? Chain rule, right? Chain rule. Times the rate of change of the inside, times the derivative of the inside, which is -1. So, what do I get? I get positive 3 over 1 minus x squared. Right, which is exactly h. So what I'm going to do, I'm going to find the power series for 3 over 1 minus x. And what am I going to do with that power series? Take the derivative, and I'll have this function, and so that'll be the power series for h. All right, so let's start again here. So I'm going to take f of x. I'm going to take, say, f of x equals 3 over 1 minus x. And what is that as the power series? Easy, right? N equals 0 to infinity of 3 times x to the n, right? A r to the n. And what I'm going to also do is I'm going to write out several terms here. I'm going to write out several terms. So you see that? Think what, right? See that? Think what? Or you're up. What would this, right? Can you give me the first couple terms of that?
3 plus 3x plus 3
Good. That's it. So it might have been better to write 4 terms, but all I had room for was 3. Okay, and so what do we say? We're going to take the derivative. So f prime, and we already did that. We found that we take the derivative of this, we get exactly this, 3 over, we get 2 negatives that cancel out, and we get exactly this. Okay, and so we're going to take the derivative in all forms, right? So what is the derivative of 3x to the n? Okay, so it's going to be 3 times derivative of x to the n. Where's Benjamin? Stritzko. Ben. We're taking attendance. We know if you're here or not. Oh, there, yeah. See, I told you. So the derivative of x to the n. Good. So we're going to do that on every term. So this is just a typical term. So every term should look like that. And so then to check it, let's do it on the terms. Derivative of 3 is 0. Derivative of 3x is 3. Derivative of 3x squared is? And let's imagine the next one. What would we have? 3x cubed. 9x squared, right? And so now we're going to look at the index and see what starting index is going to give us exactly these terms, right? So we got to make sure, so sometimes screwy things happen with the index when we do derivatives and antiderivatives. So we got to get these terms, right? So does it work if I start with n equals 0? So if I start with n equals 0, does it generate exactly these terms? Because we know these are the derivative, this is the derivative of this. So does n equals 0 generate exactly these terms? It does. In this case, also, we could just start at n equals 1 because the first non-zero term is n equals 1. So you get the same sum if you started at 0 or 1, but we'll just leave it at 0. Okay? And we know that this is equal to h. So we got it. And then we could find the interval convergence. We could find for what values of x that thing converges. And so that's where it would be equal to h of x.